Alright, today we are going to focus and talk about electron orbitals. So, the name is very misleading. Most of us, when we think of orbitals, we think of a planet circling around a sun. And for a very brief period in time, we kind of thought electrons did that around nuclei. Within, 2 years, we knew that was wrong, but the name had stuck. And in fact, the drawings for molecules that we'll usually have kind of still looks that way, even though we know this is wrong now. So we have a proton, we have an electron in its orbit on the outside. But the reality is these aren't what they look like. The electron is not a little ball that's spinning around it. When we actually think about where that orbital is, or where that electron is, it's the whole sphere. It's not a little ring around it, it's this giant three-dimensional orb with the nucleus right in the center. So when we think about where electrons are on our atoms, we can't think of them as one little point. They have these shapes, and all we can say is that they are occupying this shape. And so when we think about what electrons are doing, there's a few different shapes. If you're spherical, you are an s orbital. If your nucleus is here and you are two spheres on either side, so kind of like holding two balloons joined at the center, this is a p orbital. And if around your center you have 4 lobes, kind of like hold 4 orbital or 4 balloons together but lay them flat. Oops. This is a d orbital. And basically the 3D shape that the electron kind of spreads out over as it is bound to our nucleus generally is one of these 3. There's some other shapes, higher level orbitals, but these are the ones we're going to focus on today. The earlier elements of the periodic table only use some mix of these. So what's really going on with electrons? Well, electrons have a negative charge and your protons have a positive charge, and so they're attracted. But instead of just colliding, due to electrons having these three-dimensional kind of shapes, their wave form, we say, they don't actually just slam into the proton and stick to it. They take these orbitals around it instead. And so the electron's going to get as close as it can get. I mean, imagine you've got a mountain and a cliff and a valley, and there's a person up here, and they're throwing stones over the side. Well, that stone's going to fall. And maybe it'll get caught somewhere, but it's going to bounce, and it's going to bounce, and it's going to fill the bottom of the valley. And if you threw another stone, it's going to do the same thing, and it's going to eventually stack on top of the other one, and over time you would start filling up the valley with stones. Well, electrons are kind of the same way. Gravity pulls the rocks down, and the protons pull the electrons towards it. They're going to get as low in energy as they can. They're going to go as far down. So if we have a graph, and we say it's a graph of energy, the idea is any electron that's just kind of free floating in space and comes across your protons is going to drop down until it takes one of those shapes, till it falls into one of the orbitals. And there are other orbitals. They're spread out all over in various energies, which is just like the stones. They'll stack into higher and higher positions. Well, what this practically means is that if you have a nucleus with no electrons and you give it one, that electron is going to go and it's going to drop to the lowest orbital first. So let's make this a little cleaner again. I've got my graph, I've got my energy. The lowest orbital lowest energy you're going to have for it is called the 1s orbital. That is your lowest energy orbital. So any electron that comes in is going to go first down here. And the way we draw that is a one-sided arrow. So the electron is that one-sided arrow. Our first electron has gone into our 1s. If we add a second electron, well, the second electron is going to go down as far as it can, and you can have 2 electrons per orbital. We draw them in opposite direction. That direction is called spin. We'll discuss it another time. But as long as they're in opposite directions, you can get 2 into an orbital. Well, that's it for the 1s. There's 1 orbital and 2 electrons are in it. So if I want a third electron, well, much like those rocks that piled up higher, you can't go as far down as the earlier rocks, right? They're already there. They're taking up the space. Same with the electrons. I can't go to the 1s anymore. It's already full. I'm going to end up falling into something a little above it. And the next one above it is called the 2s. And so our third electron will fall into the 2s. Our fourth electron will fall into the 2s. So we had our first, we had our second, we had our third electron, and we had our fourth electron. Say you keep adding electrons, though. They're just going to keep stacking up. So what's the next highest orbital? Well, it varies a little bit. The next is actually a set of 3. And if we go back to our analogy, as the valley got wider, more things could be put across it before it got full. That's sort of what's happening here. As we get further away from the nucleus, as we get higher in energy, there's different ways that we can put the atoms or the orbitals around the nucleus. This set of 3 is called the 2p orbitals. And so our 5th electron would go right there. So that would be number 5. If you add a 6th, it's going to go down. It finds the 1s is already full, the 2s is already full, the 2p is the lowest that isn't full, and it's going to actually spread out first. So here's our 6th. Our 7th would go here. If we have an 8th, and a 9th, and a 10th. So they don't try to pair until they have to pair. They don't try to put 2 in the same orbital unless they have to. So they first spread out, and then they pair into those 2p orbitals. So for the first 10 electrons that you add to an atom, this is where they go. Well, what does it mean to be in those orbitals? What's going on with those orbitals? Why do we have different numbers and different letters? Let's go back and think about what the s orbital was. It's just a sphere. The 2s orbital, it's also a sphere, but it has a change in the middle. So when we draw these, when we do the math for the shape, you can have it positive or negative. And being positive or negative doesn't mean much as long as they're just different when they need to be different. So some of these will be positive, but when you cross a line, you change which you are. So the 1s is positive or negative, whichever you want, throughout the entirety of it. The 2s has a little ball of positive surrounded by a bigger ball of negative, or a little ball of negative surrounded by a bigger ball of positive, as long as they're opposite. That's what we care about. It's a slightly different shape. It stems from the math. If I've got an axis coordinate, I'm doing my math, some of it's positive and then it's negative out afterwards. So the inside looks positive, the outside looks negative, and this would be radius r. And so it basically says that anything within radius r is positive, that's here, and anything between here and here is negative. Well, that's just where it really comes from. We're not so much concerned with math as we are concerned about the order for these. Well, these are different shapes the electron takes, and different shapes just get twisted up different amounts, and they are different energies. So why is the 1s the lowest? It's kind of the simplest shape. It's just a sphere. 2s requires you to have a change, and so you've got your electron has to flip its phase as it goes from one to the other. It takes a little bit of work. It's a little higher in energy. Our 2p orbital looks like this, where one side is positive and one side is negative. Well, this actually requires a little more, it's a little more difficult to do than the flip inside. And so the 2p's are a little higher in energy than the 2s. And so we just put them a little higher. And like as we said, electrons want to go to the lowest energy, just like the rock will fall down the mountain to the lowest point. And so whatever shape is the easiest for it to do that isn't already taken is where the electron will go. Well, there's more shapes as we keep going up. And so there's a standard order that electrons will fill. It will fill the 1s, then the 2s, then the 2p's, make those equal. Next is the 3s, the 3p's, the 4s, the 3d's, the 4p's, and we'll stop there. That's enough for our purposes. This order of filling is standard for pretty much all atoms. So it doesn't matter what atom you're looking at. If you looked at aluminum and it had 13 positive charges, aluminum normally has 13 electrons to be neutral. So originally it would have no electrons in. If you gave it 1 and brought it down to aluminum 12, that 1 would go into the 1s. Your second would go 1s, your third, your fourth would go into 2s, your 5th, 6th, 7th, 8th, 9th, and 10th would go into 2p. You would just fill them in from the bottom. So if I need to go to aluminum with no charge, I need 13 electrons. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What we would find is that the last electron is sitting in a 3p orbital on its own. Well, depending what orbital your electron's in, whether they're paired, how many are there, different metals have different behaviors. So when we talk about trends in behaviors later, the orbitals affect those trends. Everything that has a full S and P but nothing else is actually a stable noble gas. If we think about helium, helium normally has 2 electrons, so it would fill the 1s, but helium was a noble gas. If you think about neon, neon has 10 electrons. Well, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Neon fills the 2s and the 2p. If the highest number, so 1 for the 1s, 2 for the 2p, the highest number you have electrons in, if you have filled the S and P and you don't have anything else, you're a noble gas. If we think about argon, it has 18 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Argon, well, its highest number that it's filling is 3. And argon has just finished filling the S and P's for 3. That's part of what helps it be a noble gas. It has just filled those. So this is the idea of the orbitals. They are just where the electrons go. There's a set pattern for filling them for most elements, and that is this pattern that we see over here. So the next bit will be easier ways to describe this, to tell where the electrons are, and then we can relate that to the behaviors we see on the periodic table, like charge. Why does a fluorine have a -1? Why does argon stay neutral? Why does a oxygen have -2? The orbitals let us explain that. So we will continue from there with our next video.